Welcome back to another video. Today we will be looking at some complex number problems, right? So let's get started with the video. So let's first focus on this question. What does this question says? Uh, there is some slight mistakes in this question also. So we'll see about that. So for the first, you have to make this correction here. It will be k from 0 to 9, right? First is this correction you have to make, and right, and nothing else. So let's get started in this problem. So we know we are being given with 11 complex numbers to be exact, right? 0 to 10, these are 11 complex numbers, and the sum of these 11 complex numbers is given as 2 raised to the power 10, right? Also, this kind of a recurrence relation is being provided in the problem. So let's work with that. So we have a recurrence relation here. Let me just write. So this is a recurrence relation. If we simplify it further, we can get 10 minus k plus 1 zk iota, and let us say we have fixed the value for z0, which we have to actually find out, right? So let us see z0. So what will be z1? Z1 will be 10 by 1 z0 iota. Next, if we see z2, it will be 9 by 2 z1 iota. That will be equal to 9 into 10 by 2 z0, right? So this is minus uh, minus, or you can say iota squared 10c2 z0. Similarly, z3 will be 8 by 3 z2 iota. That will give us 10c3 z0 iota cube. So we can say that zk is equals to 10ck z0 iota to the power k, right? Now we had z1 plus z2 z0 plus z1 plus z2 up till z10 was given 2 to the power of 10. If we fit these values, we can just get the summation. Z0 will be outside, so we can get ik k from 0 up till 10. This is equals to 1 plus I to the power 10. This gives to the power 10, right? Z0. Now let us work upon 1 plus I. So 1 plus I squared is 1 minus 1 plus 2I, that is 2I. So this is 2I to the power of 5 to z0 equals 2 to the power of 10. This gives us z0 2 to the power of 5, I to the power of 5, 2 to the power of 10. This on cancelling gives 2 to the power of 5, that is 32. I5, so I4n plus 1 is equals to I, so this will be Zi, right? So value of I z naught is equals to 32, and in this problem we were asked the value of I z naught. So the answer will be 32 to this problem, right? So 32 will be our answer to this problem, and see, it matches our answer also, right? Now let's look at the next problem here. Sorry, my health is not good today, so I have to speak a little feeble. Yes, so we have been given Zn to be, let me change the color. So Zn is given as, uh, let's see, 1 plus I, then 1 plus I root 2 till root n, and Z n plus 1 will be Zn times 1 plus I root n plus 1. So Zn plus 1 minus Zn will be Zn I by root n plus mod. Let me replace the variable here. It will be modulus of zk, k plus 1, right? Now modulus of zk, what will the modulus of zk here? Zk modulus for this problem, it will be 1 plus I modulus 1 plus I root 2 modulus 1 plus I root 3 up till 1 plus I root k modulus, right? So this will be root 2. This will be, what will be, 1 plus root 3 by 2. This will be root 4 by 3, and this will be root k plus 1 by k, right? So now these terms they cancel out till k, and k minus 1, k plus 1 root mod zk is root k plus 1. So when we substitute its value in our original equation, we get 1, right? So zk plus 1 minus zk is equals to 1. Now the problem here is the answer given is 11, but the answer given here will be, so summation k1 to 10, this will be 10. So according to me, the answer to this problem should be not 11, it should be 10, right? But according to the author, it is coming 11. I don't know how, right? So this is the solution for this problem. It is an okay-ish problem. It can come in mains. It is mains level problem, right? So it's just, you have to see the recurrence here, and you have to follow the format that is given. This one and this one is important here. You have to imagine that this will in fact turn out to be a simpler term, root k plus 1, which elegantly divides the denominator, right? So this will be, in fact, gives 1, and this will be our answer, summation 1 to 10, right? It will be 10, right? So according to me, 10 should be the answer to this problem, right? So up till now we have two problems here. Now look at it uh, look at this third problem. It is also, I would say, it is a good problem here. Now let's now here it is given Z 23, 24, 25 lie on a circle of radius. So all of them lie on the same radius to 23. Let us see. Z23, it will be 24 plus 25 plus 27, and is given 1. So this will be omega cube plus omega 4 plus omega 6, right? So let us see the modulus here, right? So yes, okay, okay, it will be plus 1 plus omega cube. Now omega 7 is equals to 1, so this means omega can be written as e to the power I 2 pi, wait, 2 pi by 7. So this will in fact turn out to be 1 plus 2 pi by 7 plus e 4 pi 6 pi by 7, sorry, 6 pi by 7. Okay. Now if we convert it into the polar form and take the modulus, we'll get cos 2 pi by 7 plus cos 4 pi 7, 6 pi by 7, sorry, squared, plus sine 6 pi by 7 plus sine 2 pi by 7 squared. On a further simplifying, we'll get 3 plus 2 cos 2 pi by 7, 2 cos 6 pi by 7, and one more term you'll get 2 cos 2 pi by 7 cos 6 pi by 7 plus sine 6 pi by 7 cos 2 pi by 7. This is the formula for cos a minus b, and it will be cos 4 pi by 7. So this term turns out to be cos 2 pi by 7 plus cos 4 pi by 7 plus cos 6 pi by 7. Now if we divide and multiply by sine pi by 7, and we open the formula for these sine a cos b formulas, and it will be, we will see that this cancels out and we get minus 1 by 2, which gives us 3 plus 2 minus 1 by 2, and this gives us 3 minus 1 root 2. So the modulus of z2 z3 is equal to the modulus of z2 z4 is equal to the modulus of z25, where it is given, that is root 2. So these lie these uh, complex numbers, they lie on the circle of radius uh, root 2. Okay, yes. So also you can try this yourselves. This is easy, right? These are 7 complex numbers and omega 7 is 1. So if omega 7 is 1, z n plus 7 is also equals zn plus 7 would also be equal to zn. So these 7 are symmetrically placed around the 2 pi angle, so they form a regular, what do you say, heptagon, right? Heptagon, they will form a regular heptagon, and a regular heptagon in a circle of radius root 2, you can say, right? Okay, you have to prove that all these numbers zn lies on a circle of radius root 2, and you have to also see that uh, area of a regular heptagon inside a circle of radius root 2. What will it be? I'm telling the answer to this bonus problem that I guess it turns out to be this. Okay, this. So you can check for yourselves. I think that this is the answer that comes out. I'm not entirely sure though. Okay, let us look at this next problem. We have done 3 problems today till now. Okay, many more to go. Okay, now we'll do this problem, this problem, and these are the problems for your practice, right? Try on your own. This is a good locus. If you see locus is asked, so it will come out to be an octagon. You have to just plot a graph and take cases like y is greater than 0, y is smaller than 0. Then in these 2 cases you have to take, actually 4 you have to take, right? For x to be uh, from 0 to 2, then 2 to infinity, then 0 to minus 2 to 0, and minus infinity to minus 2. Similarly for the negative y-axis, so it will come out to be somewhat this type of an octagon, and this will be 6, right? It will be on a circle or radius, right? Not, it is not a regular octagon, but the largest distance it will be 3. Similarly, this problem, it is a quite a tricky problem, and not a standard problem for JEE. This part, is a good problem here, right? One mistake in this problem is you have to see it is uh, it is xk greater than equal to 0, and yk does not make any difference in this problem, right? So this one is x1 plus x2 plus x3 equals to 17, where x1 x2 x3 is greater than equal to 0. You have to, you usually apply beggar coin method here, but not, the problem is different. You have to find the product of all such possible complex numbers, right? Answer is 19c5. It is a good problem. You have to try on your own. Now let us see more problems. Okay, okay. So first, let us work on A intersection B. A intersection B. We see here x square plus y. That is for A, and for B, it is 2x is equals to 3 minus y x square plus y square. If we multiply this equation uh, by what iota, right? Why are we doing this? Because we know this format can be found on like this, right? So let us see here. Okay, okay, so let us multiply it by iota. That gives us y square plus 2xy iota, and this gives us 3 iota plus x minus iy upon x square plus y square. Now this term, you can see it is just 1 by z. If z is x plus I, right, then it is 1 by z, and this is z square is equals to 3i plus 1 by z. So take z not equal to be 0. We can say that 3iz is equals to z cube plus 1 z cube minus 3iz for A union B solutions contains this. Okay, z is equals to 0 does not satisfy this equation, so we have no problem here. Okay, now for let's see for C union D. So for C union D, you can say x cube minus x cube minus 3x y square plus 3y is equals to 1, and 3x square y square 3x square y minus 3x minus y cube minus 3x minus y cube is equals to 0. Now cube terms are involved, so we can surely check out this. This will give x cube minus y cube plus 3xy iota x plus iota. This gives us 3xy square iota minus 3xy square 3x cube minus iy cube. This will give us x cube plus 3 x cube minus 3xy square plus iota 3x square y minus y cube is equals to x plus iota y. Now in these equations we know we have to multiply this by iota and then plus it and then add the equations. So it will give us x cube minus 3xy square plus iota 3x square y minus y cube plus 3y minus 3x iota equals to 1. This gives us x plus y iota y plus minus 1 minus iota. We have to take common 3, we have to take common. This will give us 3x minus x plus iota y. Okay, then equals to 0. Now this is z cube minus 1 minus 3 z equals to 0. Rearranging, z cube minus 3iz minus 1 is equals to 0. So this is for C intersection D. So as we can observe that z cube minus 3 iota z minus 1 is equal to 0 for C intersection D, and for A intersection B also z cube minus 3 iota z minus 1. Z is equal to 0, z not satisfied, so we have nothing to worry about. So we can say that the number of solutions are going to be the same as the equation, but the solution is identical, right? So we can say that n we can say that n is equals to nc. The equation of solution is identical, right? So we can say union A intersection B minus C intersection D, and means cardinality gives 0, right? 0 is the answer present in the question. Is the correct question, right? It is advanced level problem. It is advanced level problem. It will surely come in advance. Now this problem, let's see this problem also. Okay, sk, we can say that as iota e to the power iota 2 pi k as 7 6 as 7 e to the power 2 pi by 7 3r plus e to the power 2 pi by 7 r plus 1. Let us say this is our let's say this is alpha, so we can say that it is r square. This is sorry, alpha 3r plus alpha r plus 1. If we further expand, so this will give us 1, this will give us alpha cube plus alpha plus 1, this will give us 6, and also alpha 7 is equals to 0, that is obvious. 9 plus 1, 12, sorry, 15, 18. Okay, okay, okay. So let us simplify. I'm just going to copy this whole section here, and we'll going to uh, okay, okay. Let us see. 9 goes. We can write it as 2. We can write it as 5, and sorry, we can write it as just alpha. We can write this as 4. Let us look at, now I'm rearranging them in a certain fashion. Okay, copy, paste. Okay, I'm rearranging them in a fashion, if you can see. Alright, and okay, that is sorry, that is that, and probably this. Okay, okay, alright, okay, alright, alright. Let me just try to do it. Right. Now what we have done is we have made them as pairs, and we will solve each of these pairs and see what happens. Okay, this is important. It is a magical manipulation, and it will give us 9 alpha cube, alpha 5, then alpha 7, then 1, then alpha 4, then alpha 6, then 1. Right, this is 1, this is 1, this is 7, this is actually alpha squared. Okay, also 1 plus alpha squared plus, well, alpha 6, it would be 0 property it is, right? So we can check alpha, alpha 1 is present, alpha alpha is also present here. Wait, I might have done some mistake, right, sorry, this would not be 1, this will be alpha. Okay, so we have 1, we have alpha squared, alpha cube, alpha to the power 4, alpha to the power 5, alpha to the power 6, right? This gives us 0, and remains it, and what remains is this 1, this 1. Similarly, for this we have alpha 7, alpha 11, alpha 6, alpha cube, alpha 7, alpha squared, alpha 5, and 1. Okay, we have 1 here and 1 here, and this will give us 4. So we have 1 alpha, alpha squared, alpha to the power 4, alpha to the power 5, alpha to the 6, 3 also. So this also gives us this one and this one. Similarly, This gives us alpha to the 7, alpha 6, alpha squared, alpha 8, alpha 7, 1, oh sorry, alpha 3, alpha to the power 5, alpha to the power 4, 1. This is 1, this is 1, this is alpha. We have 1 alpha, alpha squared, alpha to the power 3, alpha to the power 4, alpha to the power 5, alpha to the power 6, and 1. This 1 remains. This is also give us 2, right? So this is 2, 2, 2, right? And this will be 3. When we put 0, it will be 1 plus 1 plus 1, right? For r is equals to 0. So it will be 3 into 2 into 2 into 2, that is 3 into 8, 24. Alright, so the answer to this problem is 24, and this is the correct answer. Now this problem, we are half an hour into the video, so I'd like to give this problem to you as a homework. I think the answer comes out to be 1 by 2. This is a simple problem, just you have to see. It is this also given only to confuse and just to exaggerate the extent of difficulty of this problem, as it is not so difficult problem, right? So we can say it is z1, so they lie on a unit circle. Now we can suppose this is distance between two vertices, it is fixed with the matter of rotation. Same with this, so we can suppose z1 to be purely real, and we can treat them as roots of unity, right? And roots of unity, because distance is not subjected to rotation. Okay, length, yes, length. Okay, so also, okay, this is probably uh, this you have to write zk in terms of z1, some you have to say e power I alpha, and then it will form 1 minus e to the power something like that squared. Then you have to convert it into polar form. Then you have to take the mod 1 cos alpha squared plus sine square. Then you have to see this will become 1 minus 2 something cos alpha, 1 plus it will become, I guess, 2 cos alpha, 2 2 plus 2 cos alpha it will become. And you have to just, right, you have to then take out 2 as common, and this will become 1 plus cos alpha. This will become n minus 1, and this, I guess, it turns out to be minus 1 minus of minus 1, something like that. I don't remember it correctly. Then it simplifies. This gives us n, 2n, and the above quantity also gives us n, right? Right, so this will give us 1 by 2, something like that it goes. Okay, right? Okay, here I guess only negative will come here, something like that, right? Here also negative is there, right? Alpha is something you have to take out. And this one is pretty simple. It is just, the standard z minus zk format thing, and you just have to, you know take z as a real number, right? And this is z1 is 1, as I said, to take them as a root of unity. And then you have to just the same old fashioned Zn minus 1, and then you have to do Z minus Z2, Z minus Z3 dot 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 Z minus Zn, and then we have to put Z is equals to Z1. Z1 is 1, so you just have to put right n, and something if k comes, then k also comes here, sorry, so it will give n, and n you have to, okay, yes, so this will give us n 1 plus 1 plus 1 plus 1, and we put 1 is equals to 1, right, it gives us 1 here and 1 here. So it will give us n by 2n, and limit is there, but n cancels n infinity, so it will give us 1 by 2, right, something like that. I'm not doing it completely, so I guess alright, I'm not doing it completely. So this is also your homework, right? So this is your try on your own. Yeah, this first problem, second problem, and this third problem, and there is also the bonus problem somewhere, right? Find the area, and that is answer I have already provided for all these problems, right? Answer to this is 1 by 2, 19C5 and 6 in octagon, right? So you can comment the if you have any doubt in these three problems or any other problems for the matter, right? These problems are from Namma Ganit's book, something thin book with fat ideas, I guess. uh, Good problems, but some mistakes there in the printing of the question, so I will correct if I take more problems from this book. Okay, so yes, thanks for watching, and I'll back with another video. I've been busy some with some personal matter, but yeah, I'll try to uh, make more videos and bring up with more challenging problems. I think these problems are not as challenging as VT sir, but they are advanced relevant, so you have to do these also, right? So yeah, bye, thanks for watching.